All right, today we're going to talk about a secret weapon for the IIT JEE. And no, it's not about memorizing a ton of new formulas. It's about really understanding the hidden language behind all of them, the language of units.
Come on, you know the feeling. We've all been there. You wrestle with a super complex problem, you nail all the concepts, your math is perfect, you're about to celebrate, and then you realize you messed up the units. A simple slip-up, and all that hard work goes down the drain. It is just the most frustrating thing.
And look, in an exam as competitive as the IIT JEE, that's not just frustrating. It's absolutely critical. That one little mistake can literally be the difference between getting the rank you want and missing it. Every single mark is a fight, and this is a fight you just can't afford to lose.
Okay, so here's our game plan. First, we'll look at why we even need a system in the first place. Then, we'll talk about the universal language that is SI. We'll break down the 7 and only 7 core building blocks. After that, we'll see how to build everything else from them. And finally, I'll show you how this becomes your master key to ace those problems.
So let's rewind a bit. Way back when, before we had this global standard, science was, well, it was kind of a mess.
Just imagine trying to replicate someone's experiment, but their idea of a meter was based on, I don't know, the length of some king's foot. It would be total chaos, right? This lack of a common language was a huge roadblock for scientific progress.
So, to fix all of that chaos, the scientific world basically got together and said, okay, we need one universal language for how we measure things.
And that's what a system of units really is. It's not just some random list. It's a complete, logical framework that covers literally anything and everything we'd ever want to measure in physics.
And the system that won, the one that is now used by pretty much every scientist and engineer on the planet, is the SI system. You should think of it as the official, undisputed language of physics. When you're solving an IIT JEE problem, you're speaking in SI.
Now this is where it gets really elegant. This entire universal language, this whole alphabet of physics, is built from just 7 fundamental units. That's it, only 7.
I mean, really think about that for a second. Every single quantity you can possibly measure, the speed of light, the energy from the sun, the force of a collision, it can all be broken down and expressed using a combination of these 7 base units. They are the absolute foundation.
And here they are. You already know most of these, right? The meter for length, the kilogram for mass, the second for time, of course. Then you've got the ampere for electric current, Kelvin for temperature, the mole, and the candela. These 7 are the bedrock. They stand on their own and can't be broken down into anything simpler.
Okay, so if those 7 units are the letters of our alphabet, how do we start forming words? How do we describe more complex things like velocity or force?
Well, we do that with something called derived units. These are the words of physics. They aren't new letters, they're just clever combinations of the 7 fundamental ones we just looked at.
Let's start with a really simple example, velocity. We all know velocity is just distance over time. So what do? We take the fundamental unit for length, the meter, and we divide it by the fundamental unit for time, the second, and boom, meters per second, our first derived unit. Simple.
Okay, let's kick it up a notch. Let's talk about force. We know from F equals ma that force is mass times acceleration. So, mass is a fundamental unit, the kilogram, and acceleration is actually a derived unit itself, meters per second squared. So we combine them and we get kilogram meters per second squared. Now that's a bit of a mouthful, so to make life easier, we just give it a special name, the Newton. So this really gets to the heart of it. On one side, you have a fundamental unit like the kilogram. It's a single, unbreakable block. On the other side, you have a derived unit like the Newton, which is a whole structure we built using those fundamental blocks. And here's the key. Every derived unit, no matter how complex, can always be traced back to its fundamental parts.
All right, so why does any of this matter? How does this actually help you score more marks on the IIT JEE? Because this isn't just theory, it's an incredibly powerful tool.
Think of this as your master key. For one, it lets you do dimensional analysis. If the units on one side of your equation don't match the other side, you know instantly that you've made a mistake. It's also an amazing error spotting tool. If you're solving for force, but your final answer has the units for energy, you've caught a mistake before it costs you marks. And finally, it helps you break down big, scary-looking quantities into their simple, fundamental parts.
So from now on, before you even think about plugging numbers into an equation, just look at the units. They tell you the story of the problem. They'll guide you. Seriously, just remember this. Master the units, and you master the problem.
So here's my challenge to you.
Next time you open your physics textbook, don't just read it. Go on a hunt. Find the derived units, find pressure, find work, find a momentum, and break them down. See if you can trace them all the way back to those 7 fundamental components. So what's the first one you're going to tackle?
All right, welcome to this explainer where we are going to break down the absolute fundamental tools you need to conquer one of the toughest exams in the world, the IIT JEE. So let's just jump right in with a question. Can a single millimeter cost you your dream university? In the world of the IIT JEE, you bet it can. The difference between a top rank and, well, falling short can literally come down to the tiniest of margins.
You see, we're not just learning physics formulas here. We're trying to build a mindset where precision is absolutely everything. And the very first step on that path is truly understanding the tools you're working with.
So, when you pick up an instrument, how precise can you actually be? What's the limit? Well, the answer to that is all wrapped up in a super important concept called the least count.
Think of it like this. It's the smallest tick mark on your ruler. It's the ultimate limit of that device. You simply cannot measure anything smaller or with more certainty than its least count. That's its resolution.
And this is where it gets really interesting. Look at the difference here. A standard ruler, yeah, it gets you down to the millimeter. Good enough for most things. But a vernier caliper? Whoa, that gives you 10 times the precision. For the IIT JEE, choosing the right tool isn't just a good idea, it's absolutely critical.
Okay, so you've got the right tool, you know its limit. But how do you communicate that precision to somebody else? How do you write it down correctly? Well, that's where we get into the universal language of precision, significant figures. Now, there are a few simple rules you just have to know. And trust me, for an exam like the IIT JEE, mastering these is completely non-negotiable if you want to get the right answer. So let's see them in action.
All right, let's take the number 1.020. The 1 and the 2 are non-zero, so of course they count. The 0 that's sandwiched between them, it counts too. Now the important one, that final 0 at the end. It counts because there's a decimal point. That decimal tells us the measurement was precise all the way to that spot. So that's 4 significant figures total.
Now how about this one? 0.0056. All those zeros at the front, they're just placeholders, right? They're just showing you where the decimal point is. They don't represent a measurement themselves. So you only count the 5 and the 6. That's it, just 2 significant figures.
And here is the classic trap, 73,000. Without a decimal point at the end, those last 3 zeros are, well, they're ambiguous. We don't know if the measurement was exactly 73,000, or if it was just rounded to the nearest thousand. So, to be safe, we only count the digits we're 100% sure of, the 7 and the 3. That's 2 significant figures.
But here's the reality check. No measurement is ever perfect. And the IIT JEE doesn't just test if you can do the math, it tests if you understand this uncertainty. You have to know how to handle the 2 main types of errors you'll run into.
So here's the breakdown. Systematic errors are consistent. Think of a scale that's not zeroed properly. It's always going to read a little bit high. It pushes all your results in one direction. Then you've got random errors. These are the unpredictable little fluctuations. Maybe your hand shakes a tiny bit or there's a draft. They create a spread of data around the true value.
The theory's great and all, but let's get our hands dirty and see how we actually quantify these errors in a real problem.
And this table shows the process perfectly. You don't just measure once, right? You take a few readings to help cancel out those random errors, you calculate the mean, which here is 5.22, then you figure out the average error, and we get 0.013. We round that to match our mean, and boom, there's our final answer, 5.22 plus or minus 0.01 centimeters. That tells the whole story, our best guess, and how confident we are in it.
Okay, so we've covered least count, we've covered significant figures, and we've covered errors. Now for the main event. Let's put it all together and see how it works in a typical exam-style problem.
Here we go, a classic question. You're giving 2 measurements, length and width, and asked to calculate the area. But pay attention to that last part, the part that trips people up. Reported to the correct number of significant figures. That's the key.
So, step 1 is always the easy part. You just do the straightforward math. Don't even worry about the rules yet, just multiply the numbers.
You punch it into your calculator, and it spits out this long, pretty number, 33.800. And it looks so precise, right? But this is where you have to be smarter than your calculator. That number is lying about how precise the measurement actually was.
Which brings us to step 2. We have to apply the rule. And for multiplication, it's pretty simple. Think of a chain. A chain is only as strong as its weakest link. Well, your calculation is only as precise as your least precise measurement.
So let's check our links. The length, 10.4, has 3 significant figures. The width, 3.25, also has 3 significant figures. So our weakest link is 3 sig figs. That means our final answer must also be rounded to 3 significant figures.
So, we take that 33.800 from the calculator, we round it to 3 figures, and we get 33.8. That is the correct final answer. Anything more would be wrong because it would be claiming a level of precision we just didn't have. You know, this quote really says it all. In the IIT JEE, almost right is just plain wrong. Mastering these tiny details about precision is what separates the people who get top ranks from everyone else.
Because, look, mastering these concepts isn't just about passing some exam. It's about learning how to think like an engineer, how to think like a scientist. Precision is the foundation. So the real question is, what are you going to build with it? All right, let's jump right in. If you're gearing up for a huge exam like the IIT JEE, you know that every single second, every single mark is absolutely crucial. So today, we're not just flipping through another chapter in a textbook. Oh no, we are unlocking a secret weapon, a tool that's going to save you time, stop you from making silly mistakes, and give you a massive advantage.
So let me ask you this. How can you spot a wrong physics answer in just 10 seconds? Seriously, you're staring at 4 options. They all look incredibly complex, and you just don't have time to redo the whole problem. How do you find the fake and fast? Is there a cheat code?
Well, yes, there is. The answer lies in the dimensions. It's this beautiful fundamental principle that's kind of hidden in plain sight. And trust me, once you learn to see the world in terms of its basic dimensions, like mass, length, and time, you will never be able to unsee it.
To really understand why this is such a game changer, we have to put ourselves right in the middle of that exam hall. You know the feeling.
Picture this. You're in the exam. The clock is ticking, loud. You've just spent 10 minutes on a really tough problem. You get an answer, but something just feels a little off. Is it option A or is it option B? They look almost identical. And you know that one wrong choice could mean negative marks. That's when the pressure hits. That's when most people panic. But not you. Not after this.
The reason you won't panic is because we're about to look at physics' fundamental recipe. We're going to understand the core ingredients that make up every single formula you've ever seen.
I want you to imagine that every single concept in physics, velocity, energy, momentum, you name it, is like a complicated dish from a fancy restaurant. No matter how complex that dish seems, it's always made from just a handful of basic core ingredients. And that idea is the key to everything.
And here they are. These 7 quantities are the fundamental building blocks for literally everything in the physical universe. But here's the good news. For most of mechanics, and for 99% of what you're going to face in an exam like the JEE, you really only need to care about the big 3. Mass, which we note as m, length, which is L, and time, which is T. Everything else is just a combination of these 3.
So when we write out that recipe for any quantity using these M, L, and T symbols, we call it a dimensional formula. It's nothing fancy. It's just the ingredient list. It tells us exactly how many parts mass, how many parts length, and how many parts time you need to build that quantity.
So how do we actually find that recipe? How do we decode a quantity? Let's get our hands dirty and break one down, step by step.
We're going to take something that seems kind of abstract, right? Force. But you're about to see that dimensionally, it's incredibly simple. All we have to do is follow a few logical steps.
It's a really simple 4-step process. First, we start with the formula everybody knows, F equals ma. Step 2, we break that down into its most basic parts. Mass is already a fundamental quantity, but acceleration is really just length divided by time squared. Step 3, we swap in our dimensional symbols. Mass becomes m, and acceleration becomes L t to the minus 2. And finally, step 4, we just clean it up. We multiply them together, and there it is. The dimensional formula for force is mLt to the minus 2. And that's it. That's the recipe. So here's the beautiful part. It doesn't matter what kind of force it is, gravity, friction, tension, anything. Its fundamental dimensional DNA is always mLt to the minus 2. Always.
Okay,
So we know how to find the dimensions. Now it's time for the payoff. This is where all that theory turns into your secret weapon for the exam hall.
This one skill has count 'em, three incredibly powerful applications that are going to be your absolute best friend when the pressure is on.
Number 1, and this is the big one for exams, you can check if an equation is even physically possible. This is the fastest way to eliminate wrong answers. Number 2, you can actually derive the basic form of a formula if you've forgotten it. And number 3, you can handle any unit conversion without breaking a sweat.
And this, right here, is the magic trick. It's based on something called the principle of homogeneity, which is a fancy way of saying, for an equation to be true, the dimensions on both sides of the equal sign have to be exactly the same. They have to match. So look at the left side. Someone says velocity equals acceleration times time squared. Let's check. The dimension for velocity is Lt to the minus 1, but the right side simplifies to just L. Wait a minute. Lt to the minus 1 is not equal to L. It's like saying seconds equals meters. It's nonsense. That answer is physically impossible. You can cross it off the list. Now look at the right. V equals AT. We check the dimensions, and they match perfectly. This is how you spot the wrong answer in 10 seconds flat.
The second application is a total lifesaver. Let's say your mind goes blank in the exam. It happens. You can't remember the exact formula for the period of a pendulum, but you do remember it has something to do with the length L and gravity G. Well, just by matching the dimensions, knowing you need to end up with time on one side, you can figure out that the period has to be proportional to the square root of L over G. You can literally rebuild formulas from scratch. It's amazing.
And the third one makes unit conversions completely foolproof. Forget memorizing a bunch of random conversion factors. When you need to go from, say, meters per second to kilometers per hour, you just focus on converting the L component and the T component separately. You can build the right conversion factor from scratch every time and never make one of those silly mistakes again.
So let's just zoom out for a second here. Let's talk about the big picture, about what it means to start thinking in dimensions.
What we've really been talking about here are your new exam superpowers. You can now save critical time, you can slash the number of little calculation errors, and maybe most importantly, you start to build a deeper intuition, a gut feeling for physics. You'll start to be able to just look at an answer and know if it feels right or wrong.
So please, remember this. Dimensional analysis isn't just another trick or a chapter you have to get through. It is a lens. It's a fundamental way of thinking, of looking at the physical world and seeing the elegant, consistent structure that lies underneath all the complexity. And mastering this won't just boost your scores, it's going to boost your confidence.
And that's our explainer. But I want to leave you with a final thought. This core principle, this idea of dimensional consistency, it doesn't just stop with physics. It works in chemistry, in engineering, you can even apply it in economics. So now that you know the rules of the game, my question to you is, where else are you going to use them to find the answer?